Ever found yourself pondering why we can't reach the speed of light? It's a question that has puzzled and intrigued thinkers and scientists for centuries. In the vast expanse of the cosmos, the speed of light is the ultimate limit, a boundary that no object or information can surpass. This universal speed limit, clocking in at roughly 186,000 miles per second, is a cornerstone of our understanding of the universe. According to Albert Einstein's theory of relativity, nothing can travel faster than light. This theory, which revolutionized physics, has held up against a century of rigorous testing and scrutiny. But this limit raises a perplexing question. In a universe where we've broken so many barriers, why does this one remain? What's so special about the speed of light that it remains an unreachable frontier? So, why is the speed of light our cosmic speed limit? Keep listening to find out. To answer our question, let's dive into a fascinating concept called time dilation. It's a mind-bending phenomenon that has its roots in Einstein's theory of relativity. But don't worry, we're not about to get lost in a sea of complex equations. Instead, let's take a more intuitive approach. Imagine you're on a train, racing down the tracks at a significant fraction of the speed of light. Now, this isn't your average commuter train, but bear with me. As you sit there, sipping your space coffee, time for you is ticking away normally. Your watch, your heartbeat, everything is the same as it would be if you were sitting at home. But here's where it gets weird. An observer, let's call them Sam, who is sitting at the train station, has a different perspective. When Sam looks at your watch, they see it ticking slower than their own. Sam's heartbeat, the birds flying in the sky, everything around Sam is happening faster than what's happening on your train. To Sam, it's as if time on your train has slowed down. This is the crux of time dilation. It's the difference in the observed time measured by two observers due to a relative velocity between them. In simpler terms, the faster you move, the slower time passes for you compared to a stationary observer. It's a strange concept, right? But it's a fundamental aspect of our universe, a universe where speed limits aren't just for the highway. Now you might be asking, what does this have to do with the speed of light? Well, as your train speeds up, time for you slows down even more. And if your train could reach the speed of light, then time for you would stop completely. That's right, time would literally stand still. So, if you're racing at nearly the speed of light, time would literally slow down for you. It's a head-spinning idea, but it's at the heart of why you can't reach the speed of light. But we'll delve more into that in the next scene. For now, just remember, in the cosmic race against light, time is not just a spectator, but a key player. Now, how does time dilation prevent us from reaching the speed of light? Well, let's dive right into this fascinating conundrum. As we inch closer to the speed of light, time dilation, this peculiar effect of the universe, becomes increasingly noticeable. You see, time dilation is the idea that time isn't a fixed constant. It can stretch and contract based on how fast you're moving. Imagine you're on a spaceship zooming through the cosmos at a speed close to that of light. To you, the ship's clock appears to tick normally, but to a stationary observer back on Earth, your clock is moving painfully slow. This is time dilation in action. Now let's push this concept to its limits. What happens if we somehow reach the speed of light? Well, according to the theory of relativity, time for the moving observer, that's you on the spaceship, would come to a standstill. A second on your spaceship would become an eternity to the rest of the universe. But here's the catch. This scenario is purely theoretical. In reality, we face a significant barrier. In order to reach the speed of light, an object would need infinite energy, which is practically impossible. And even if we ignore the energy problem, there's another hurdle. The laws of physics as we understand them today simply don't permit time to stop. Time, it seems, must always march forward, regardless of how fast or slow it might appear to different observers. So, reaching the speed of light presents us with a paradox. On one hand, it requires infinite energy, something we just can't muster. On the other hand, it demands that time stop, something that goes against our current understanding of the universe. In other words, to reach the speed of light, we would need to stop time, which is a feat beyond our grasp. But what does this cosmic speed limit mean for us, you may wonder? Well, the implications are as boundless as the universe itself. To begin with, the speed of light sets the scale for our universe, acting as a cosmic yardstick against which we measure everything else. Imagine if we could travel at light speed. We could zip around, visiting distant stars and galaxies with ease. But alas, the universe isn't designed for our convenience. The speed of light is a hard limit, forever out of our reach. This limitation on speed, in turn, limits our ability to explore the cosmos. Even with our fastest spacecraft, it would take tens of thousands of years to reach even the closest galaxy to ours, Andromeda. Yet, these limits also lead to some of the most fascinating phenomena in physics. Take time dilation, for instance. The faster we move, the slower time appears to pass for us relative to a stationary observer. This isn't just a theoretical prediction. It has been tested and confirmed with extremely precise experiments. And then there's length contraction. The faster you move, the more squished you appear in the direction of your motion, at least to a stationary observer. These phenomena aren't just mind-bending quirks of the universe. They have real-world implications. Global positioning systems, for instance, have to account for time dilation effects due to the high speeds of the satellites and their relative motion to the Earth. If they didn't, your GPS would be off by miles. These implications of the light speed limit serve as a humbling reminder of our place in the cosmos. They remind us that the universe dances to its own beat, not ours. Our job is to understand and adapt to the cosmic rhythm, not to try and force it to match ours. So, while we may dream about traveling at light speed, the universe has its own set of rules, and understanding these rules helps us better comprehend the fascinating cosmos we inhabit.